Welcome to Ask and Learn.
We want to sketch the graph of y is equal to x squared over x squared plus 3. So in this chapter, we are given this laundry list of steps we should follow. So we're just going to go and do them step by step. So the first one is to find the domain of our function. Well, rational functions, the only thing we ever have to worry about is when our denominator is equal to 0. But in this case, x squared plus 3 will always be greater than or equal to 3. So our domain is just going to be all real numbers. The next thing we want to find are our intercepts. So let's go ahead and find our x-intercept first. So x-intercept will be where y is equal to 0, so we get x squared over x squared plus 3. Now there's nothing I can ever plug into the denominator to make this equal to 0, so I just set the numerator equal to 0. And so that tells me x is equal to 0. And since we know this, we already know our y-intercept as well, since x is equal to 0 would be where our y-intercept would be. So we don't even need to find our y-intercept since it would be the same as our x. The next thing we want to do is look for symmetry. Well, rational functions are not known for being periodic. So we should check to see if it's even or odd using f of negative x. So plug it in negative x, we get negative x squared over negative x squared plus 3. And that would simplify to x squared over x squared plus 3, which is equal to f of x. And that's going to imply that we have an even function. And even functions are symmetric about the y-axis. So symmetry across y-axis. So with that, if we just graph one side of our function, we can just reflect it across the y-axis to get the other side. Now the next thing we're going to want to look for is asymptotes. So since the denominator can never equal 0 in this rational function, we're not going to have any vertical asymptotes, but since the power is the same or the largest power, I should say, is the same, we know that as x approaches positive or negative infinity, that this should be where we just divide the coefficients of our polynomial, or of the largest degree of each. So we have 1 over 1, which is 1, and remember, we just know this from chapter 2.6. So we have a horizontal asymptote at y is equal to 1. All right, the next thing they tell us to do is to look for intervals where the function is increasing or decreasing. So I'm going to go ahead and group that in with finding our local max and min, since those two things do go hand in hand. So let's go ahead and find the derivative of this first. So we have y is equal to x squared over x squared plus 3. Now to take the derivative of this, we're going to need to use quotient rule. So quotient rule says low d high minus high d low all over, that was low again, so x squared, so low d high minus high d low all over the square of what's below. So x squared plus 3, and then we need to square that. Alright, now we know the derivative of x squared is just going to be 2x. Again, the derivative of x squared is going to be 2x, and the derivative of 3 is just 0. Now let's go ahead and do a little bit of algebra, and once we simplify everything, we should just be left with 6x over x squared plus 3 squared. Now, we can go ahead and set this equal to 0 to find our critical value. So again, nothing I ever plug into the denominator will make this function equal to 0, but we can set the numerator equal to 0 to find our critical points. So I do 6x is equal to 0, which would just imply x is equal to 0 will be our critical point. All right, so let's go ahead and write that over here now. So we have y prime is equal to 6x over x squared plus 3 squared. So now, to figure out where our function is increasing, we want to find where y prime is strictly larger than 0. And this is going to be on from 0 to infinity. Then we want to find where this function is decreasing, which would be where y prime is strictly less than 0. And that's going to be from negative infinity to 0. Now let's go ahead and put our critical point down here and use the first derivative test to figure out if this will be a max, min, or neither. So to the right of x is equal to 0, the function is increasing. To the left of x is equal to 0, the function is decreasing. So that tells us at x is equal to 0, we have a local min. So we know our origin is going to be a local min. And the last thing they tell us we should find is the concavity and any inflection points we may have. So we're going to need a second derivative to do this. So let's come over here. So y double prime is going to be equal to, so I'm going to factor that 6 out to start. And then to take the derivative of x over x squared plus 3 squared, we're going to have to use quotient rule again. So again, it's going to be x squared plus 3 squared times the derivative of x minus, in the opposite order, so x times the derivative of x squared plus 3 squared all over what we have in the denominator squared, which would now be to the 4th power. Now the derivative of x is just going to be 1. The derivative of x squared plus 3 squared, well, first we're going to have to use power rules, so that would be 2 times x squared plus 3. And then we have to take the derivative on the inside, which is going to be 2x. And now if you were to go through and do that algebra, we should end up with 18, 1 minus x squared over x squared plus 3, and now cubed. All right, so again, we can go ahead and set this equal to 0 to try to figure out our possible points of inflection. So that would tell us we need to make 1 minus x squared equal to 0, or x is equal to plus or minus 1. All right, so we're going to need those values in a second. All right, so we have y double prime is equal to 18 times 1 minus x squared over x squared plus 3 cubed. And we're going to want to find where this is concave, which is where y double prime is strictly greater than 0. And this is going to be on the interval -1 to 1. Then we want to figure out where this is concave down, or where y double prime is strictly less than 0. We're just going to be negative infinity to -1 union 1 to infinity. And if we go ahead and put those 2 points that we found earlier, and then see if we have a change in concavity, we can determine if these are going to be inflection points or not. So on -1, or negative infinity to -1, the function is decreasing. On -1 to 1, the function is concave up, and I meant to say concave down to the left of x minus 1, not decreasing. And to the right of x is equal to 1, the function should be concave down. So we have change of concavity at both these, so we know both these points should be points of inflection. And so that was the last thing they said we should do before we actually start graphing this. So let's go ahead and start plotting some points. So we know our intercept should be 0, 0. So we can put that. Our asymptote would be at y is equal to 1. So y is equal to 1 is our asymptote. We know at x is equal to 0, we're going to have a minimum. So we don't need to figure out what that value for y is, or if it's above or below our horizontal asymptote, since we already know it's 0. And we know at -1 and 1, we should have a change in concavity. All right, so let's go ahead and start now. So we can start from this minimum we know, and we can keep on going until we hit -1, and then we should have a change in concavity, and then we'll go and get as close to our horizontal asymptote as we can from the bottom. And then we can just go ahead and reflect this across. And actually, let me move 1 a little bit closer, just so it actually does look a little bit more symmetric. Right, so just reflecting across the y-axis, it should now look something kind of like this here. So from -1 to 1, that is definitely concave up, and to the left, it is concave down, and to the right of 1, it is concave down as well. So looks like we have everything we need. You could go in and maybe say what -1 and 1 are if you really want to be specific, but as far as I'm concerned, all we really need to know is the shape at each of those points, and just adding anything more is just extra information at this point.